Welcome to DigiDig, where we uncover the past and explore the future.
At 13,000 feet above sea level, the Andean Altiplano is a punishing environment. It is a high, arid steppe defined by freezing temperatures, thin air, and desolate rocky terrain. Yet, during excavations at sites known as Wilamaya Patjxa and Rewrote Patjxa, archaeologists found human remains buried in this hostile zone. 9,000 years ago, ancestral Aymara foragers, including individuals named Warawara and Foxy by local communities, made their permanent homes here. Surviving in a frozen, low-oxygen wasteland requires extreme biological and behavioral adaptations. Based on what was pulled from the dirt, scientists arrived at a very logical conclusion about how these early populations lived. The graves contained highly specific, lethal artifacts. Archaeologists unearthed heavy stone hide scrapers and sharp projectile points. These weapons were found alongside the shattered, butchered bones of large, high-altitude mammals like the vicuña. The traditional consensus formed quickly. To survive this environment, early humans had to be specialized apex predators, consuming an almost entirely meat-based diet. But there is a fatal flaw in this logic, known as preservation bias. Stone tools and dense animal bones endure for millennia in the soil. Soft plant tissue rots away. The dirt of the Andes told a highly compelling story of a meat-eating society. That story, however, was built entirely on the fragments hard enough to survive the passage of time. To test the dirt story, modern science relies on biogeochemistry. Researchers look deep inside the cellular structure of ancient human bones to find the truth. Through a process called Stable Isotope Analysis, scientists can read the specific chemical signatures left behind by the foods a person digested over their lifetime. This chart showed how isotopes track diet. One of the key markers is nitrogen. Due to trophic enrichment, nitrogen levels spike the higher an animal sits on the food chain. Given the abundant spears and animal bones, the skeletons were expected to hit the absolute top of the scale. This isotope test pitted a century of archaeological theory against hard molecular evidence. When the data came back, the skeletons failed the apex predator test. Their nitrogen levels were incredibly low, dropping into the herbivore range. Then, measuring carbon isotopes revealed their signatures locked perfectly onto highland C3 vegetation. Statistical mixing models crunched the chemistry to provide an exact ratio. The diet of these supposed big game hunters was 80% plant matter and only 20% meat. That 80% majority came directly from wild tubers, the hardy ancestors of the modern potato. Beyond the chemistry, researchers found direct evidence in the soil, microscopic bits of charred tuber tissue preserved in ancient fire pits. The skeletons themselves displayed highly specific, severe dental wear on their front teeth, a mechanical record of a lifetime spent chewing gritty, starchy roots. The fierce, spear-wielding hunters of the high Andes did not run on big game. Their society was economically powered by the potato. Why would a community with the weapons and skills to hunt large mammals choose to rely so heavily on digging up tubers in a frozen wasteland? At 13,000 feet, the human body suffers from hypoxia. It is a constant state of oxygen deprivation that makes every action a metabolic struggle. Biologically, the body requires less oxygen to metabolize carbohydrates than it does to break down proteins and fats. In an environment where every breath is a struggle, tubers provide more energy for the same amount of oxygen. Meat was still necessary to secure specific micronutrients, like vitamin B12 and iron. Hunting served as a vital form of nutritional insurance, rather than the main caloric engine. The wild potato was the specific tool that made permanent life at these altitudes possible. With 80% of the diet coming from the ground, the traditional hierarchy flips. In the Andes, the term hunter-gatherer is being replaced by gatherer-hunter. It reframes our understanding of prehistoric labor and gender. Gathering was the true foundation of survival, making hunting a shared secondary task. A century of our scientific understanding was warped by the simple fact that stones survive while plants decay. For generations, we defined our earliest ancestors exclusively by the weapons they built to kill. When we look closely at the chemistry of their bones, we learn that humanity is defined by what we cultivated and understood. History is often written by the victors, but in archaeology, it's written by what doesn't rot. At nearly 13,000 feet above sea level, the Andean Altiplano is a harsh, hypoxic expanse. For decades, researchers have worked to understand how the very first human populations survived in this environment 9,000 years ago. The initial evidence suggested a survival strategy dependent on meat. Excavations recovered hundreds of stone projectile points, scrapers, and knives, tools designed for hunting and processing large game. But this conclusion relied on the physical durability of stone. Inorganic materials like projectile points and dense animal bones are resistant to decay, persisting in the soil for millennia, while soft plant matter rots away almost immediately. Because the physical record is heavily skewed toward materials that survive decomposition, it provides a distorted view of the actual prehistoric diet. Correcting this distortion requires a shift away from the macro world of traditional artifacts and toward the chemical forensics of the human skeleton. Inside analytical laboratories, researchers look past the physical tools and examine the human remains themselves. Specifically, they extract and target ancient bone collagen from the skeletons recovered at the Wilamaya Patjxa site in Peru. This collagen acts as a molecular ledger. Because of the biological mechanics of digestion, atoms from consumed food are permanently incorporated into the skeletal structure of the consumer. To read this ledger, scientists use an isotope ratio mass spectrometer. Inside a high vacuum chamber, a bone fragment is rapidly dissolved and vaporized, breaking the sample down into its elemental components. The machine isolates and counts two specific chemical markers, stable isotopes of carbon and nitrogen. Stable isotopes are non-radioactive variations of an element. They retain the same chemical properties as standard elements, but differ slightly in their atomic mass, meaning some atoms are measurably heavier than others. By calculating the precise ratio of these heavy and light isotopes in human bone, scientists can reverse engineer an entire dietary ecosystem without requiring a single physical scrap of ancient food. The analysis begins with the first elemental marker, nitrogen-15. This vertical diagram illustrates a species' trophic level, which is a metric of its exact position on the food chain, ranging from plants at the base up to apex predators at the top. Nitrogen isotopes measure this level through a process called trophic enrichment. With every step up the food chain, the heavier nitrogen-15 isotope bioaccumulates, increasing in concentration within the consumer's tissues. If the humans at Wilamaya Patjxa were the big game hunters their stone tools implied, their nitrogen levels should theoretically register at the top of the scale, alongside other apex predators. The spectrometer data revealed the opposite. The human nitrogen levels fell short of the apex predator zone, landing near the bottom of the scale in the herbivore tier. When these isotopic signatures were compared against local high-altitude herbivores like the vicuña, the nitrogen levels were remarkably similar. The nitrogen data mathematically precludes a carnivorous lifestyle. To identify what these human populations were actually consuming, researchers had to examine the second half of the chemical ledger. The focus then shifts to the second chemical marker, carbon-13. Carbon isotopes track the base of the food web. They differentiate food sources by identifying the specific photosynthetic pathways utilized by different types of plants. This split-screen graphic contrasts two major plant groups. C4 plants, like tropical grasses or maize, carry a high carbon-13 signature. C3 plants, which include high-altitude shrubs and tubers, carry a distinctly low carbon-13 signature. The carbon data extracted from the ancient bones formed a perfect statistical match for the C3 photosynthetic pathway. In the ancient Altiplano, the primary carbohydrate-dense C3 resource was the wild tuber, the biological ancestor of the modern potato. This chemical evidence aligns with biological records. The ancient individuals exhibited distinct wear patterns on their teeth, a mechanical marker of lifelong processing of gritty, starchy tubers. Carbon data confirms the consumption of potatoes, and nitrogen data rules out a reliance on meat. However, raw isotope ratios alone cannot define the exact proportions of a mixed diet. Researchers faced a final technical hurdle, converting these raw atomic mass ratios into exact dietary percentages. To solve this, they utilized Bayesian mixing models, advanced statistical algorithms designed to untangle complex isotopic mixtures. Before calculating the human diet, the algorithm first requires a complete baseline database of the local ecology. This biplot graph maps that ecological baseline. The model is fed baseline isotopic data from dozens of local sources, plotting C3 plants, C4 plants, and large mammals into distinct clusters based on their carbon and nitrogen signatures. The ancient human data points are then plotted onto this exact same matrix. They land securely between the plant and animal clusters. The Bayesian algorithm cross-references the human points against the ecological baselines. It runs thousands of probability simulations to determine the most statistically likely combination of food sources. The model returns a precise dietary split, 80% C3 plants and 20% terrestrial meat. 4/5 of their caloric intake was derived from gathered plants, reducing hunted meat to a distinct minority of their diet. That remaining 20% of meat provided critical nutritional insurance. Large mammals supplied essential amino acids, iron, and vitamin B12 that tubers lack. The 80% carbohydrate load fulfilled a strict physiological necessity. In conditions of extreme high-altitude hypoxia, the human body demands high glucose carbohydrates for energy generation, prioritizing them over fats and proteins. The Bayesian model resolved the mathematical dietary ratio, and in doing so, detailed a highly optimized biological survival strategy, engineered for one of the planet's harshest environments. Applying these microscopic data points to the Andean Altiplano forces a correction of the historical record. For over a century, the standard historical model for Andean survival placed the hunt at the center of human development. By relying on visible, durable artifacts, early archaeological interpretations unintentionally established a male-centric narrative of survival. The chemical data overrides the physical artifacts. The colonization of the extreme Andes was powered by the predictable gathering of wild potatoes, not the unpredictable hunting of big game. This data is supported by the remains of specific individuals like Warawara, a female hunter buried with a complete arsenal of weapons. Her existence dismantles the assumptions of a strictly gendered division of prehistoric labor. And yet, even Warawara, an equipped big game hunter, was shown by the mass spectrometer to have consumed an 80% plant-based diet. Stable isotope analysis and Bayesian modeling establish a rigorous standard for evaluating human history, relying on chemical evidence that is immune to physical decay. The later shift to formal agriculture grew out of a long-term mastery of a plant-based economy that had already sustained these populations for millennia. Thank you for digging deeper with us. Subscribe to DigiDig to uncover more of history's greatest mysteries, solved by tomorrow's technology.
Thank you for watching.